I know that in the audience there's at least a couple of folks who've been eagerly waiting for his talk. And you may recall, right, when we still had in-person conferences, his presentation was always, among the most well-attended ones. No pressure, Dan. No pressure. For those of you who don't know Dan, he's our spatial solution specialist, and he is typically working with large global customers and also strategic partners to solve all kinds of challenging spatial requirements, typically related to scalability. Now, Dan, are you ready? Are you there?
Yeah, I'm here. Hey, Hans.
Hey, good to see you. Right. So then, take it away. The floor is all yours.
Share my screen.
That looks good.
Hey, can you see that okay?
Yeah, that's fine. Great.
Excellent. All right. Thank you, Hans, for the introduction. And my name is Dan Geringer. I'm a spatial solutions specialist, part of the Oracle Spatial Development team. And my session is going to be on optimize Oracle spatial performance, best practices, tips, and tricks. So what was nice, the sessions that you've had so far have been no code and low code, really great sessions. And some of the stuff I'm going to talk about is actually used by some of those no code and low code environments. And some of it that I talk about will just benefit those environments in general. So with that, I will kick it off. So this, I always like to do a little slide that's just the features of Oracle Spatial. Certainly, around here, you can see we support points and lines and polygons. We have location tracking, network models for drive time analysis. We have GPS tracking analysis, address geocoding, and topologies, LiDAR, LRS, raster, but lots of different features. And we also have some services that were being used by those components that you saw earlier, mapping services, geocoding, routing, OGC web services, and Spatial Studio. What I'm going to focus on today is going to be on vector best practices, so vector analysis. So Oracle Spatial data and data models. So some of the things, especially for maybe there's some new people on the session today, some of the things that we've always done is made sure that our spatial data stored in database tables with the same security, high availability, manageability, data integrity, and scalability as non-spatial data. And some things that we can leverage out of the box, some native features are things like TDE or transparent data encryption, data redaction, active data guard, replication, parallel query, and more. So it's part of the kernel, Oracle Spatial, and it leverages all these and integrated with all these key features. Like I said, vector, raster, GPS tracking data, LiDAR data, network model. My best practices is going to focus today on the vector. So vector data, simply ordinary Oracle tables, no such thing as a spatial table. You can have one or more geometry columns. I heard that was talked about today too. Points, lines, polygons can be stored in that geometry column. Ordinary data modeling concepts. So normalized tables is what we recommend. So very often, sometimes you see in data warehouse applications where, joins might introduce overhead that people don't want. I've seen people denormalize tables. Not something you really want to do that we recommend doing with spatial data, because what that does is it repeats the geometry column. And spatial, we have a lot of really neat and powerful spatial features, and I'll actually talk about some of those today. Some have already been talked about, but in general, spatial computations are a little more intense than just regular, character string comparisons. So you don't want those more intense computational geometric computations to occur on denormalized tables where geometries are repeated. It actually would slow things down. So we don't recommend denormalize. Some key things to always do is, validate your geometries, make sure they're valid. If they're valid, then we guarantee correct answers. Spatial indexing for fast performance, and spatial queries from my experience, most of the time, the spatial predicate is the most selected predicate in a query. So here, we're just showing you a little bit about a spatial operator. So you've got points, lines, polygons stored in a spatially enabled database, indexing to make it happen faster. And here's a within distance spatial operator. What I like to just show here is that I like to think of the operators as having a template. The first argument of a spatial operator is always the column that you're searching. It's the spatially indexed column. The second argument is a query window or an area of interest. And the third argument is going to be a string that's specific to that operator. In this case, within distance, we're taking a path of a hurricane, which could be a line, and buffering it by 10 miles, and then searching the first argument. So all the templates, whether it be, all of the spatial operators, whether it be within distance, any interact, they all have that model, that same template. First argument, the column you're searching. Second argument is your query window. And here, after it does the within distance and finds all my policyholders, you can select them into the select list and generate a report. So with that, I'm going to go into another very scalable feature of the database called table partitioning. And it's something that can be very, very effective with the Oracle Spatial. So generally, when I work, like as Hans said, I work with customers with very large data sets, sometimes billions of records. So generally, if tables start exceeding 50 million rows, that's a good sign for me that partitioning is probably going to help, right? But I found many cases where even much, much smaller, way smaller than 50 million rows, where you can have very effective applications where you can really leverage partitioning, and it can be very effective too. So first, let's talk about temporal partitioning. I think that's very common, especially with GPS data and any kind of temporal data coming in over time. Very important for two reasons, manageability and performance. What does manageability do for partitioning? And this isn't even specific to spatial. Manageability gives you very easy ways to bulk add new data quickly and age all older data out with features of partitioning called exchange partition and drop partition. So those work with spatial too. What you do is you create a local spatial index, and it enables you to do these very manageable things with your spatial data too. But for performance too, and especially for temporal data, because a lot of times temporal data is geometries coming back to the same area, but just on a different day. So you end up kind of stacking geometries in the same region. And if you don't partition it, when you do queries against that, just think about it. You're doing that, those queries, even if you're interested in only maybe a one-day slice, the geometry analysis is happening against the whole stack of the data across all the time, right? And if data came back to the same region, so that's not optimal. A very easy way to solve that is just do temporal partitioning, partition by time. And that way, when you do your predicate for time, it's going to basically do partition pruning and only look at the partitions that you want and only do that more costly spatial analysis against those partitions. So temporal data is really, really important thing to keep in mind for partitioning. So also I've had customers that I work with like utilities. So I had a utility that I worked with and they stored all their data in a single table for all their feature types, which was great for when they wanted to do a query that says, okay, show me all my assets in this region. And it just basically searched them all out. But then they came back and said to me, Dan, I'm trying to do a query where I just want to see manholes, or I just want to see transformers, but it's taking longer than I expect. I said, you know why? When you do your spatial predicate, right, the spatial index is only a spatial index. It doesn't, if you put a different predicate on there, like feature type, that doesn't get propagated into the index. It first has to do spatial portion of the query. And that spatial portion, if you have all your feature types in the same table, is going to go against all your feature types, right? And that could be, once again, more geometric computation you want to do. But just imagine what I told them, I said, how about partitioning your table? And this is a table example that was nowhere near 50 million rows per partition or exceeding 50 million rows. But I said, how about if you took your table and just partitioned it by feature type? Now you've got each partition is a different feature type. And when you say, show me all of my manholes in this region, where feature type equal manhole, it's only going to look at that partition. And especially if you have a local partition spatial index, very, very effective. So partitioning can be very key to performance. We support, in earlier releases, we only supported range partitioning, but for anyone that hasn't visited partitioning lately, we now support just about every combination: range, hash, list, interval, reference, composite, range, hash, etc. Right? And the key is when you create your partition table, don't forget at the end of the create index statement to specify that local keyword, so it'll create local partitioned spatial indexes. So I mentioned earlier geometry validation. That's really important. I can't tell you how many times I go in and work with a customer and they say, oh, I'm not getting the result I thought I was going to get, or this isn't working. First thing I do is validate. I run a validation, right? And the rules we use are not ones that Oracle made up, right? These are based on standard organizations, the OGC consortium. So standard geometry validation. Some common issues that I see: repeated consecutive points in a line or a polygon, self-crossing polygons, and invalid geometries may result in incorrect results. So it's very important. There's built-in validation routines to validate your geometries in spatial. One is called validate geometry with context. And then we also have some built-in routines to fix geometries, like rectify geometry. Oh, we have another one I didn't put on here. It's called self-union, SDO self-union. So those are some utilities I use sometimes to fix geometries. They're not magic. You know, they can't fix everything, but they do pretty well. The fastest way to validate geometry, so it's all about performance, right? So if you have lots of geometries that you want to validate, this is a very similar approach to calling the function geom.validate layer with context. But by doing it this way, you will get the best performance. So if you, the inner select here in the red box is basically taking all of my roads and pumping it into the validate geometry with context. And I'm also selecting the row ID pointer. And then on the outer part of the subquery, I'm selecting the row ID and the STO row ID and the status from this validation, but I'm only storing in the validation results the ones where the status is not equal to true. And you can do a parallel degree here, and this scales really, really nice, very linearly. Well, if I do a top on the machine, I can see all those cores go straight up, however many I use. So it's important to have the resources you want. That's one thing I always tell people. When you're doing parallel, parallel works great with spatial. It's very linear, but you need the resources. In other words, if you're on a machine that's already bogged down, parallel is only going to hinder that more. So you want to make sure that you have the parallel resources. And if you do, you can really, really maximize throughput. And maybe you only need those parallel resources for a short amount of time, and then they're freed up for whatever else. This is a kind of neat thing, right? So when you're working with longitude, latitude data, we always used to say that the smallest tolerance that we support because of our algorithms was 5 centimeters. Now we support smaller than 5 centimeter tolerances. Now, why is that important, right? I come across, like I said, customers with data that's invalid. The first thing I go and look at it, they're not getting the results they want. Then I look at their data's invalid. And the first thing I try to do with them is, hey, let's go try to fix this. And we've got utilities like rectify geometry, remove duplicate vertices, right? But what I noticed lately is, since now we support smaller than 5 centimeter tolerances, one of the things I do right up front is before I start fixing, I'll just try a smaller tolerance. Maybe I'll try 5 millimeters. And when I do that, just by making that tolerance smaller, many of the repeated duplicate vertices go away. Self-crossing intersections, they just go away. So it's really nice that we can go smaller than 5 centimeters now. So I think it is important. Just one little last bullet there. Oops. All right. A little sensitive on the mouse here. So when you do change your tolerances, whatever tolerance you choose to use, make sure that you're consistent across all the layers that you plan to compare, right? You should have a consistent tolerance across all your layers. just a slide that shows, I talked about a template earlier for SEO within distance. First argument is always the column you're searching. That's the spatially indexed column. Second argument is your query window, and then a string that's specific to that operator. These are all other operators within Spatial. All of them follow that same template. Inside touch, any interact, within distance, nearest neighbor, all follow that template. Spatial vector acceleration. This is something we introduced a few years back. It is an initialization parameter. It's a very important initialization parameter. I can't tell you, even my most experienced customers, I'll go and they're having a problem. I'll get on a call with them. We'll do a Zoom conference. And the first thing I'll say is, can you show me the value for spatial vector acceleration? And they go and they show it to me. And sometimes it's false, even though they're like, I know you said it so many times. I don't know how it got false. Sometimes it's as simple as when someone set it to true, they didn't do scope equals both, so it didn't go into the SP file. So rebooting the database came back with the old default, which is false. This is so, so important. The reason that this parameter actually exists is because Spatial used to be a licensed option. Right? So in December of 2019, Spatial became a feature of the database, which means you no longer need a license to use Spatial. Everyone can use Spatial, right? So it was a way to delineate. So by default, we didn't have this parameter set to true because only licensed customers could use it, but that no longer is the case. So now it's an education thing. We're trying to educate everybody. First thing you check, every user benefits, make sure you check that that parameter is set to true. Make sure it's set in your SP files. Everybody can use Spatial on all databases, right? So it's also a different code path. So you want to really make sure, because if you run into an issue, the first thing support's going to say is it's set to true, because we're not really addressing issues in the old code path anymore, right? So it's only in the spatial vector acceleration true code path. I believe it's 21C that now it is by default set to true, but I've got so many customers that are still on 19C, and believe it or not, still on 12C, where the first thing they have to do, they need to make sure, because the default is false. So you want to set it to true. A lot of major optimizations with that. So if your query window, remember I told you the template of a spatial operator, the first argument is the column you're searching. The second argument is your query window or your area of interest. With spatial vector acceleration equal to true, we have algorithms that are so much faster. We do major optimizations when the query window is a polygon, especially a high vertex polygon. So this is a time zone polygon. I zoomed in here so you can see the detail. This is a 343,000 vertex polygon, and I can use it to search other layers, right? And with spatial vector acceleration turned on, my queries were 300 times faster. So very key. You want to make sure that that is turned on. This is a very nice support note. So I want to mention it to everybody. It's called doc ID, and there's that number 2514624.1. And it's all about the direction of Oracle, Oracle Spatial, which is DBRUs natively have inclusion of spatial patches needed by most. And that's the goal. And that's where we are now. With 1914 and beyond, the DBU, when you apply a DBRU alone, it includes spatial updates needed by most. But for releases prior to 1914, it's very key that you apply the spatial patch set described in this document. So this document is a live document. It's maintained by Oracle support, and it's DBRU specific recommendations for spatial patches to apply. It's live, which means that when new DBRUs come out, this document will get updated. And when spatial patches to apply are superseded, this will also get updated. So it's a nice document. It's live. Keep checking it. Like I said, 1914 going forward, just upgrading your DBRU is going to be enough for most, but there'll always be some one-off patches that come out that you may need. And we will try to make these available through this note right? The most common ones that we think people need. And the goal is that the spatial specific DBRU patches that we list in this document are always going to be targeted for inclusion in the next DBRU. So the next DBRU when you apply it will likely contain the patches, but there is a cutoff. So depending on the cutoff time, it might not be that next one, it might be the subsequent one, right? But the key is now, very nice that we've mainstreamed patching into just the DBRU process. Spatial data organization on disk. So this is a really nice feature, and it's something that really does help performance. And I'm going to talk about some strategies to do this. So spatial indexes, right? How do you do this? Spatial indexes themselves are organized by default, but the spatial data that that index points to generally is not organized by default. So how do we get them in sync? And why is it important? Why is it important, right? Spatial indexes store in a secondary table managed by Oracle. Our spatial indexes are stored in a secondary table managed by Oracle, and you probably have seen these MVRT dollar tables, right? What does the spatial index store in there? It stores the minimum bounding rectangle of a geometry, along with pointers back to the base table that contains the data, right? The spatial index itself clusters those MBRs close to each other in the index. So when you do a spatial search, it can quickly find things, nearest neighbors or other geometries close by really quickly. But what if it has those pointers to the actual base table, and that data in the base table isn't clustered together? Basically, things that should be close to each other might be in different parts of the disk, different database blocks all over the place. But that results in lots of database block gets, right? So if there were a way for the spatial data to be organized on the disk, where spatial data close to each other is on the disk in the same block, then when you did spatial queries, there'd be much fewer database gets and much faster performance. So that's why it's important, right? So the solution is to order by a linear key. So let's talk about what that means and reduce these block gets. So spatial data organization on disk, two strategies. I'm going to have a strategy I'm going to talk about for point-only data and a strategy for lines and polygons. What I found recently is that Oracle has a solution, and it's not spatial. It's called attribute clustering, right? It's a very nice thing that you could use outside of spatial for the same reason I just described. It gives you the ability to cluster your data on disk, even for non-spatial data. This is a built-in Oracle feature, attribute clustering. I'm going to show you how to use it, and it can be used for any spatial point data or only point data. For lines and polygons, because the attribute clustering doesn't support objects, right? We're going to use a different way. We're going to use a spatial function called linear key, and I'll discuss both of these strategies in the next few slides. So first I'll talk about point-only data. We're going to use this feature called attribute clustering. So interleaved attribute clustering, not spatial specific. You do have to store your point as, not as an STO geometry. You have to store it as two number columns, right? X1, Y1, longitude, latitude, you decide. It's got to be two number columns, right? And then if you're storing data as two number columns, we're going to actually talk a little bit about this in this presentation. We're going to talk about creating a spatial index, a spatial function-based index on those number columns. But this clustering is not limited to just clustering on the X and Y. Like I said, it can be used without spatial. And if you have a temporal column, a time column, I found it super effective to cluster on all three. So you could say cluster on time, X and Y. And I'll show you an example of that too. So assume that your point data is longitude, latitude. All you have to do is append to your crate table this clause, clustering by interleaved order, longitude, latitude. If you had a temporal piece, you could say time, longitude, latitude, and then yes on load. And I'm going to show you an example on the next slide. So here I have a table, create table. This is for GPS tracking data. So I have a couple of columns here, user ID, a capture time, a longitude and a latitude. And then I'm going to add this clause. I'm going to say no compress, no logging. And I'm going to add this clause, clustering by interleaved order. And I'm going to use capture time, longitude, latitude, yes on load. It's as simple as that. That's all you have to do. And then Oracle manages the clustering for you on load. So attribute clustering is not available, is only available, I'll put a little comment here, for direct path insert operations. And the direct path insert can be selecting from either an external table or a regular table in Oracle that's not clustered, right? So the from is just selecting from some table. And we're going to be inserting into a new table called the track table in this example. And the key is that I needed to do direct path. So I'm going to use this append hint. You could also use parallel query, not required, but it does help, right? And I'm just going to select the data and it's going to do it. It's going to do this clustering for me. Nothing I need to do, but benefit from it later on when you do your spatial queries. So that was for point data. Now let's talk about for non-point data or for line and polygon data. For that, we're going to use linear key. So for lines and polygons, we're going to use a spatial function called linear key instead. So linear key is based on gridding a coordinate system. So I like to think of it as, think of a piece of graph paper on your coordinate system. And you're going to have cells. And you basically are going to decide the size of the cells on that piece of graph paper. And the clustering is going to happen on those cells. So every cell in the grid has a unique key. What this function does is you pass it a point and a size, and I'll tell you a little bit more about the size and picking the size in an upcoming slide, right? You pass it a point and a size, and it's going to bring back a cell ID. So it does the translation and figures out the unique key for the cell in that grid, right? So given a point as input, the function returns that key, that cell ID that the point falls into, of the cell that that point falls in. So for lines and polygons, you have to choose a point, right? So we're not going to cluster every point on a polygon or every point on a line. You have to just choose one point. It can be the first point. It could be the center point. So I generally use the first point, and I'll show you that on the next slide. And we're going to cluster the polygons or lines based on the first point of the geometry. So an insert ordering by linear key will optimally cluster line and polygon data on disk. I'll give you an example. So here I have a table, create a table called ship tracks ordered. Ship tracks ordered, and I have my table here in the red says ship tracks not ordered. So my ordered table, it's going to have all my columns in it. And these are lines, ship tracks are lines. And I've got my geometry column, and I have an ID column. So I'm going to select in the first red box here, this is a query subfactor query with the with clause. So with part one, I'm going to do this query where I'm just going to select all of my ship tracks that are not ordered. And I'm going to select the columns in that table. You can have column 1, column 2, however many columns you have. Your geometry column. And then I'm going to call this function in Spatial called point on surface. What it does, if you haven't ever seen it, it really just returns the first point of a geometry. So I'm going to pass it the geometry. I'm going to call it first point. And then this subquery is going to come into the outer part here. I'm going to select the same columns, select column 1, 2, the geometry column. I'm going to use SQL Analytics here, this row number, because I want to do an order by linear key. An order by linear key, I'm going to be selecting from part 1. I'm going to alias it to P1. I'm going to take that first point. I'm going to pass in P1, that first point's X value, its first point's Y value. You give it the coordinate system bounds. In this case, it's longitude, latitude. So it's -180, -90, 180, 90. And this number 22, which I'm going to discuss in a little bit, is where you pick the size of the cell for the clustering. And by doing this with statement, so think of this as a template. You can use this template, right? Just store it along as a template. You can use it, and I'm going to be inserting data into a new table that's going to be ordered by linear key. And believe me, it's kind of neat. If you just do a select on the table and look at the geometries as they get selected, you'll see that they come back close to each other, which means that on disk, they're being stored close to each other. So one of the key things that we talked about was attribute clustering to store points. But I said to do that, you have to store your points as an X column and a Y column, not as a geometry. Well, how do you create a function? How do you create an index on that if I don't have a geometry column? Well, this is going to show you how to do that. Spatial function-based indexes for tables with no geometry column. So this is designed for uniform geometry. So function-based indexes, first of all, is not a concept that's a spatial concept. You can create function-based indexes on non-spatial data too, and it's very common. We can also create spatial function-based indexes. And the reason would be for a table that doesn't have a geometry column where you still want a spatial index. So for uniform geometries, where the geometry that you're modeling has the same number of vertices in every row. So points definitely have an X1 and a Y1 in every row. If you have 2-point lines, you can use this strategy as well, because every row will have an X1, a Y1, an X2, and a Y2. Or box polygons, because every row will have a min X, a max X, a min Y, and a max Y. So these are all candidates to use for spatial function-based indexes. And the steps are simple. I'll highlight them here, and then I'll show them to you in the next slide. So first is create a function that returns a geometry, populate user SDOGeom metadata, create the index, and run queries. That's it. So first thing is we're going to do step one, which is create a function. So we're going to create a function. We'll call it getGeometry. It passes in a longitude, a latitude, or an XY, you decide, right? And really, it could almost be a one-line function. I put some extra stuff in here, but really what it's doing, it's returning an SGO-geometry constructor, 2001, an SRID. In this case, I'm using 4326 for longitude, latitude, an SDO point type constructor. And I'm just taking these values, the longitude and latitude, and stuffing them in here. So it's really kind of like a one-line function. I just put some error checking in here. I put error checking. I said, if the longitude passed in is null or the latitude is null, then return null. Otherwise, return a geometry. This is going to give me that mechanism to be able to have this function called on values that are not geometries, an X and a Y, or longitude, latitude, and create a geometry. So this is just creating the function. I have a note down here that says anytime, and this is important, not just for spatial function-based indexes, but any function you write that returns geometry objects, you should declare them as deterministic. Parallel enable is nice too, but deterministic is really important for query performance. So if you already have functions that return geometries, go back and check them and make sure that they're declared deterministic. Really important. Step two is populate user SDOGeom metadata. So this you're probably all familiar with, insert into user SDOGeom metadata. Normally you populate a table name and a column name. Well, instead of a column name, we're going to populate the function with the parameters. And these are the actual column names in your table. So I have a table called with a column called longitude and latitude. So my getGeometry function. So normally you populate a table name and a column name. Instead, we're going to do a table name and the function that returns geometry. And in the metadata, you must put the owner of the function. Very important, right? And the rest is the same. It's just the access information in the coordinate system. And then step three is create the index. Normally a create index statement is create the index on a table name, on a column name, on table name, and then open parenthesis, the column name. Well, we don't have a geometry column. We have a function that returns a geometry. So we can recreate the index on this function, getGeometry, which we pass longitude and latitude. And then index type is mdsys, that's spatial underscore index. I'm going to use the V2 because I'm going to talk a little bit about a new index type. I'm going to talk about in the next slide or next couple of slides. It's called the CV tree index. So when you create spatial function-based indexes, it works on both R-tree spatial indexes and CV tree spatial index. Both are supported. I'm going to talk about the benefits of a CV tree spatial index. But basically, if I didn't put the CV tree index equal to true, it would create an R-tree index. By putting it equal to true, it's going to create a CV tree index. It's an optimal point type index, and we'll talk about it in a second. Always for point data, specify a layer G type equal to point. It will make your queries against your point layers run faster later. And step four is just running a spatial query. So I have a track table I can do with any interact. Normally, like I said with the template before, the first column is usually a column with a spatial index. Remember, I don't have a geometry column, but my first argument in this case could be the function that returns the geometry, because I do have an index, a function-based index on that. So I'm searching this get geometry longitude, latitude. Second argument is my query window equals true. So it's very simple to do, very simple to set up, and very powerful. And complements things like attribute clustering, like we talked about earlier. So the CB tree spatial index that we talked about before, optimized for streaming point data, optimized for ingesting stream point data with the spatial index enabled. That's what this was designed for. It's designed to hand concurrent DML from multiple sessions, for example, a connection pool, much better than an ordinary R tree index did. So really for large point data sets of data streaming in, CB tree is what you want to use. It's and also much faster spatial index creation, much faster DML, and much better support for concurrent sessions inserting into that same table with that spatial index enabled. No spatial functionality is compromised. And all you have to do is specify CB tree index equal to true. That's it. And index type, instead of being just mdsys.spatial_index, you have to put _v2. V2 is this CB tree index is a feature of _v2 spatial indexes, which are system managed spatial index.
Dan, sorry to interrupt. We're getting close to the top of the hour, so we have like 5 minutes left.
I'm actually going to do one quick thing and split parallel query for now. All this is in the presentation. I do want to talk about spatial clustering. This will take me probably about 3-4 minutes. Is that all right, Hans?
Yeah, fine by me.
Yeah, so this is really, really cool stuff. So spatial clustering for trend analysis. So trend analysis could be telematic clustering. And this is where I come into working with customers with huge amounts of data, all right? And telematics could be something where GPS points are collected in billions, right? It's very effective to cluster and generate much more manageable data sets for analytics. Identify patterns or trends associated with that cluster data. It's much more manageable to do it on cluster data than on the billions of records, right? Clusters at a particular time of day, so you can actually do temporal clustering. I'm going to show you an example of that too, and store that information and do some trending analysis. So this is very fast, what I call server-side parallel-enabled clustering. Cluster millions of rows in seconds, so you can actually do it on the fly. I had 1 million points. I was able to cluster it into 62,708 clusters in under a second using 16 cores. So you can do it on the fly, or I can cluster 1 billion points into the same 62,708 clusters in about 7 minutes, parallel 16. What does it do? It returns the center of the cluster and a count. So once again, it's going to use that same function we talked about earlier, the linear key function. You have to pick the size that you want to cluster things to. So if you said, if this is my entire coordinate system, size 1 would be 1/4 of the size of the coordinate system. Size 2 would be 1/16 of the coordinate system. Size 3 would be 1/64. So you're just decomposing. It's a quad tree kind of decomposition. So that you just use this number, it's going to be passed to linear key, and it defines your cluster size. And it's as simple as I have my 1 billion row table here, and I'm calling every row in there is going to get clustered by this linear key. I'm going to select the longitude and latitude from the billion row table. I pass it the extent of the coordinate system, and this number means divide down 14 times. This was 3 times, 4 times. You go down, and you could just determine what the size of that tile would be. The function returns the ID of the cell that that point fell in. So it generates this ID, of which we have these decoding functions, like linear key center. You pass it the cell, and it'll bring back the center of the cell. We also have linear key boundary, which will bring back the extent of the actual cell as well. And now that as every point is getting clustered, I could do a count star and a group by cell ID. And basically, I'm going to have the center of every cell, how many points fell in that cell, because I'm grouping by cell ID. This could be an example on a road network, things that got clustered. So I kind of thematically mapped larger circles, means 68 things got clustered here. This would be a great example for apartment rentals. So if rental apartments were available, maybe 68 were available here, 4 here, 2 here. So I'm clustering. Where it falls short, and I'm almost done, Hans, believe me. Where it falls short is if you want to cluster GPS data, because it's so for apartment rentals, it makes sense, right? But if you think about GPS data, where you have a single person reporting lots of points, so this you could tell is kind of like on a road network. So cars driving through and GPS positions being collected. So if the same person is in this region right here and stays there for a while, a lot of their points are for that one user. So really you need a second step in the clustering process where I want to identify for GPS data the unique ID of the person that fell in that cluster. So here's an example. It's actually, I'm going to show you this last example here, right? It's accomplished 2 things. I'll do that clustering, but I'll also add a temporal component. So I have my innermost piece here, I have my 1 billion row table, but instead of just selecting the linear key on longitude, latitude, and getting the cell ID, I'm also selecting a user ID, a day, so there's a reported time. I'm extracting the day out of it, and I'm extracting the hour of the day. So I have that day and the hour of day. On the outside here, I'm selecting the cell ID, the user ID, the day, and I'm making hourly ranges. So I'm saying if the hour was between 0 and 6 a.m., let's assign that range number 1. It's between 6 a.m. and 10 a.m., and I'm going to give it the number 2. So I'm assigning these ranges. And then I'm going to basically cluster on the cell ID, the user ID. The key is I don't want to have that user that's reporting its GPS position multiple times be counted multiple times. By grouping on the cell ID, a user, a day, and an hour range, every user will only have its count in there one time, right? And now I can do a second group by, which will now make sure that each user, when I have these counts, are going to be associated with distinct user IDs. So 68 different cars came through here. But now I can do really powerful trend analysis. I can say from the center of this location where 68 cars went through, at 8 a.m. in the morning, I want to do a query and find against a whole different layer. So I want to do a query against maybe Yellow Pages. What kind of businesses are within here? Why are cars coming in here at 8 a.m.? Why are so many cars coming through here? And you could do an analysis and say, oh, nearby there seems to be a Starbucks, right? So people are going to where the donuts are, right? So you could do this trend analysis very easily with this clustering analysis. So that is pretty much it. We've got some resources here in the presentation and Q&A.
Brilliant, Dan. That was very interesting. I really enjoy your presentations all the time, and I'm sure many folks on today's call do that as well, which is why we still have so many folks on the call. In the interest of time, I think we'll have to move the Q&A or any kind of question to the Slack channel. Let me just quickly take over the presentation. So if there are any questions to Dan, do stick them into the Spatial channel in the Slack workspace, which we've shown you earlier on. As you can guess, there's loads of interesting stuff which Dan could potentially talk about. He's got many more best practices and tips and things which are useful for working with spatial data, optimizing spatial data management, optimizing performance. And if anybody on that call here would like to see more similar presentations in the future that dive into more of these topics, do please drop us a line. You can do that now in the Q&A, or even better, put it into the Spatial channel on the Slack workspace. That would definitely be helpful. We're thinking of setting up more regular calls like this from our end, not necessarily tied to the analytics and data Oracle user community, but more for educational purposes. So if there's anything you want or anything you need, do let us know. And with that, this was the last session for today. Thanks a lot, again, Dan.